4.4 optimization problems. Students will be able to analyze a problem, write a function to model the problem, and then use these techniques known from previous sections to find the max or min values, i.e. optimize the function to justify your solution. Okay, so the figure to the right shows the graph of f prime, the derivative of a twice differentiable function f on the closed interval -3 to 4. The graph of f prime has horizontal tangents at -1, +1, and +3. The areas of the regions bounded by the x-axis, that will be irrelevant at this point. We haven't gotten to the area under the curve quite yet. So part A, find all x-coordinates at which f has a relative maximum. You have a reason for your answer. Okay, so f will have a relative maximum when the derivative, so f has relative maximum when f prime goes from positive to negative. Okay, and that happens, it looks like at x equals -2. It doesn't look like that happens anywhere else. It looks like there would be a min value potentially at x equals 4 if the graph continued like that. Okay, on a graph of f prime, f is concave down if the second derivative, okay, part B, f is concave down if the second derivative is less than 0. Which implies, okay, so the second derivative is less than 0. Let's highlight a couple of spots. Second derivative would be the slope of the first derivative. So there and there. That would be where the graph of f is concave down. Okay, so that implies that the slope is decreasing. So f is decreasing means f prime is less than 0. So what we want is we want concave down and decreasing. So we want to know where the second derivative is less than 0, and we also want to know where the first derivative is less than 0. So the second derivative is less than 0 and the first derivative is less than 0 here, and it's also true there. So the values for which this would be true, where the function f is decreasing and concave down, would be between -2 and -1, as well as between 1 and 3. Alright, so for part C, find the x-coordinates of all points of inflection. Points of inflection happen when the second derivative goes from negative to positive or positive to negative. The other scenario in which that happens is when f prime changes from increasing to decreasing, or decreasing to increasing. So on our graph, we can see that f double prime, right, changes from negative to positive there, positive to negative there, and negative to positive there. So we would have points of inflection at -1, 1, and 3. So x equals -1, +1, and +3. Okay, so this second example says find two non-negative numbers whose sum is 10 and whose product is a maximum. Alright, so I've written out the sum of the two numbers x plus y equals 10, therefore y equals 10 minus x, and their product would be p of x, which is x times y. Now I want to replace this y to make it in terms of x so that I can optimize and maximize this product function. So p of x would actually be x times the quantity 10 minus x. So p of x in expanded form would be 10x minus x squared. We do need to have some kind of restrictions on this. We know that x has to be positive or non-negative, and x also has to be less than 10, right? It wouldn't make sense. So now let's go ahead and let's find the critical values. Let's find p prime of x, which would equal 10 minus 2x. Let's set that equal to 0. And clearly x would equal 5 would be a critical value. So on a number line, I'll just go ahead and plot this. We'll go ahead and plot. We know that x equals 0 is a 0. We know that x equals 5 is a 0. We know that neither of our values can be negative. So do we just need to test these two intervals? So we want to find whether or not p prime is positive or negative here, and the same thing here. So you could take p prime of 1 and p prime of, let's say, 6, and you'll notice that this one would be greater than 0 and this one will be less than 0. So how do we define a maximum, right? We define a maximum by the derivative going from positive to negative at that point. So since we have a derivative positive then a derivative negative, we know that we will have a max. P of x will have a maximum at x equals 5. So from the original sum equation, we knew x plus y equaled 10. Therefore, if x equals 5, then y also equals 5. And so the max value of our product would equal 25. Oh my goodness. Alright, so in example 3, Farmer Best has 10 meters of wire with which he plans to build 2 identical adjacent pens as shown. What are the dimensions of the total enclosure for which the area is maximized? What is the domain? Okay, so we're going to assume that these two lengths are pre-existing, some kind of wall or something to that effect. The area of this enclosure, the area will equal x times 2y. Okay, so let's also talk about the total amount of fencing, or let's see here, yeah, the 10 meters of wire fencing. Well, we know those 10 meters would equal 2 y's plus 3 x's. So what I'm going to do is isolate this y by in the length function on the right side over here. I'm going to isolate y and substitute it in right here for the y in area, and then we're going to optimize area. And so then we're going to determine and turn this into an area function based on x. I'll do that off camera and come back with an answer. Okay, so I solved for y over here. I plugged it in for y here. Notice I brought that 2 over. The 2 would cancel with that 2. X times 10 is 10x. X times negative 3x is negative 3x squared. So before we move forward, we got to talk about the domain for x. The domain for x would require x to be between 0 and 10/3, or 3 and 1/3. The reason why it could not be equal to 3 1/3 is if I divided that 10 meters of fencing between these three values for x, I wouldn't have anything left for y. So this is our domain right here. So just understanding that if we get a value where the derivative is equal to 0 outside of that, we don't need to consider it at all. So let's find the derivative, which would equal 10 minus 6. 6x, okay, which would tell me that if I set this equal to 0, that looks like x would equal 10/6, or if we simplified it, x equals 5/3. Since 5/3 is within the domain that we have shown, we would check our endpoint at 0, which clearly the area, if x was 0, would be 0. So that's not going to be a max. So we would check again the derivative of somewhere between 0 and 5/3, and then on the endpoint over here, I believe 3 1/3 is, well, it won't even matter, right? We wouldn't need to check, this isn't going to be 0, so we wouldn't need to check anywhere to the right over here because the derivative does not equal 0 there. So we just have to check within these two values here. All right, so I'm going to do f prime of, let's say, 1, and we'll go f prime of 2, and we'll figure out whether those are positive and negative. And it does look like this comes out to be greater than 0, and this comes out to be less than 0. Therefore, we can say that there is a maximum here at x equals 5/3. So the area function has a maximum at x equals 5/3. So that max area would equal x, which is 5/3, times 2y, which of course we determined was 10 minus 3x, so we would go 10 minus 3x over 2. I almost forgot the 2 out in front. We get 2 times 5/3 times, this comes out to be 5/2. These 2's will cancel, and it looks like we get a max area of 25/3 meters squared. That's our max area. Okay, so in this AP example, it says consider a triangle on an XY plane. Two vertices of the triangle are on the x-axis at 1, 0, and 5, 0, and the third vertex is going to be somewhere along this curve here, right, on this domain of 1/2 to 8 on that curve. That curve is given by the following equation. So we want to maximize the area of that triangle, choosing a point somewhere on that curve. So what we're going to do is, over here you'll notice that I set up the area formula. The base of this triangle will always be 4, the distance from here to here. The height will be whatever the y value is, or the output of that. So I've generalized that, right, using y equals that equation over here and distributing a 2 to all terms. So if I took the derivative of the area function, I would get 1 over 2x times 2. Okay, times 2 again. So this 2 is that one, and then the derivative of the inside using the chain rule is the second one. Minus 1, it looks like, okay, because the derivative of negative x is that. Okay, so we'll get a cancellation of one of these 2's. So it looks like the derivative of the area function will be 2 over x minus 1, which would equal 0. Right, this would equal 0 when x equals 2. Okay, so we've got some critical points here. We got endpoints. We want to know what the area would be when we're at either of the endpoints. And then we want to know what the area would be at our critical point, right, where x equals 2. So as we look at these three outputs, we see 19/2, we see 2 natural log of 4 plus 8, and 2 natural log of 16 plus 2. The maximum value out of those three is this one, so the area will be maximized when the x value is 2. That would be our area, and C would be our answer. Have a great day. That'll be 4.4 optimization.